Okay, we're now going to look at a simple demonstration of the technique called TLC. That doesn't mean tender loving care. It means thin layer chromatography. And before we get started, here I'd like to show you what I mean by thin layer. We buy glass plates, one of these out of here, that are 20 by 20 centimeters. And on them they have a very thin layer of silica gel. You know about silica gel. It usually comes with electronic instruments that you buy, and there's a little packet of silica gel in there which absorbs moisture. Well, this has the same property, only this is very, very finely divided. And then what we do, okay, let's put that back in there, is to cut them apart with a glass cutter, just like a glazier would do, and we then show them to you in this particular form. Here are some TLC plates that have been cut up into various sizes. The most common one we have here is about 1 inch by 3 inches, as you can see. But we have other sizes in here. But this is the way you'll see them when you come into the lab. We'll get back to that in a minute. Thin layer chromatography is used for separating compounds which have varying degrees of polarity. The surface of the silica gel, the silica itself, is a polar substance, and it hangs on to polar molecules more strongly than it would less polar molecules. And we're going to spot them on we're going to spot our solutions of molecules we want to separate on a TLC plate, and we're going to put them in an eluting solvent that is going to cause the samples to migrate up at different rates up these plates. Okay. Now what I've made are two solutions. This is called fluorinone. I like fluorinone because you can always tell where it is. It's a nice bright yellow compound. And we're going to separate it from benzoic acid. Here's benzoic acid. It's a white material. You won't be able to see it progressing up the plate, but we'll point that out a little bit later. Okay. We get them from our stock containers. This is fluorinone. And here's benzoic acid. They're not very expensive materials, so we buy them in bulk. Okay. And the solvents that we're going to use are the ones that I show here. For instance, this is hexanes ethyl acetate. It's a very common mixture of two solvents. We call it 9-to-1. In other words, we use 9 parts of this volume-wise to 1 part of ethyl acetate. So hexanes ethyl acetate 9-to-1 means 9 hexanes, 1 ethyl acetate. And we're going to increase the polarity, as we'll see in our experiment. This is 8-to-2 or 4-to-1 hexanes ethyl acetate, so it has more of the polar ethyl acetate than the hexanes. And then we're going to go all the way up to 6-to-4, so it's 3-to-2 hexanes ethyl acetate, so we're increasing the ethyl acetate component. And then the last one we're going to look at is then hexanes ethyl acetate 4-to-6 or 2-to-3. So in these bottles we're now going to have solvents which go from low polarity to higher polarity. And we're going to show that we can separate these two compounds, fluorinone and benzoic acid, on the basis of their own polarities in these solvents. Well, what are we going to use to separate them? Well, we're going to spot these on TLC plates, as I'll show you in a minute, but we're going to use what we call developing chambers. Here is a glass tube. You might say it's got a, you can see it's got a piece of filter paper in the bottom of it, right there. And I'll show you. See, there's a piece of filter paper, and that fits exactly on the bottom, and it has a plastic cap on it to prevent evaporation of the solvent during the determination. Now I've got these marked 9-to-1, 8-to-2, 6-to-4, and 4-to-6 as the solvent that we're going to use for developing what's called the eluting solvent is going to be changed. How much do you put into these developing jars? Well, you can see from this one that I previously filled, this has 10 milliliters of 4-to-6 hexanes ethyl acetate. So that's probably about 3 to 4 millimeters depth. And so I'm going to fill each one of these. We use 10 milliliter graduated cylinders for this because they're just simply easy. That number is easy to remember. Okay, so I'll just fill up this one. You get to do this so many times that you develop a feeling for how much solvent you actually need. Okay, so there's 10 mils of the 9-to-1, and I'm going to put it in the developing chamber. Got to get this off. These fit very tightly, and let's put that in there. Just put this over the top again, and I usually slosh it around so that the vapors fill the chamber. So there's our 9-to-1 hexanes ethyl acetate developing solution, and I'll put approximately the same in volume in each one of these. As I said, 10 is not a magic number, but 10 is a number that you should kind of remember. If you put too much solvent in these, you'll see that you will not get a good separation. If you put too little of it, there's a chance that you don't have enough and your sample is not going to be separated properly. Okay, so there's 6-to-4. Put the top on that. And finally, we'll do 4-to-6 again. When you're doing this, make sure that you do this in a hood, because these solvents, while they're not particularly poisonous, should not be breathed. So working in a hood is always the better of two options. Okay. All right. So now we have our 4 solvents: 9-to-1, 8-to-2, 6-to-4, and 4-to-6. What we want to do now is to spot these dilute solutions that I showed you before of fluorinone in methylene chloride and benzoic acid in methylene chloride. The reason that I use methylene chloride, by the way, is because it is a very volatile solvent, and it has solvent power to dissolve most polar and nonpolar materials, as it turns out. And so when you're doing this sort of thing, you ask yourself, what kind of a solvent do I want to use? Well, you can use just about any solvent as long as it dissolves the material and is volatile. Okay. All right, so let's take out our plate. And I'm going to take out these 1-inch by 3-inch plates here, because we got to put 3 spots on them. And I'll take out 4 of them. Whoops. Got to be careful here. Okay, here we have. Okay, we have our 4 plates. Now I want to mark them in the following way. We want to make sure that the place where we spot the TLC plate is about 1 centimeter from the bottom. That is where this enters the solution that we have over here in our developing chamber. And I'm going to do like carpenters do, and I'm going to run my lead pencil. Don't use a pen for this sort of thing. Use a pencil. Run it across there. If you're a little squeamish about getting cut by glass, don't worry. Nobody's ever been cut by glass. And I'm going to put 3 vertical lines through there. So what you have then is a horizontal line that runs right across the bottom of the plate, about 1 centimeter from the bottom, and then 3 lines. Notice I got these lines in close enough so that they're not at the edge. If you spot on the edge of a plate, you get what's called an edge effect. And that is an improper travel of this material up the plate as the solvent advances. So we try to keep that away from the edge to avoid edge effects. And I'm going to label these fluorinone, benzoic acid, and then the middle spot is going to be a combination of fluorinone and benzoic acid, and you'll see why we do that in a minute. So that's going to be 9-to-1. And if you're careful, you can use pencil on these, which will not dig into the plate. What you don't want to do is to chip off the silica gel that's on the plate. So there's our 9-to-1. Let's do an 8-to-2. Do the same sort of thing, the old carpenter thing. One, fluorinone, fluorinone plus benzoic acid, and benzoic acid. Okay, there. Third, 6-to-4. Line again. Okay. And 1, 2, 3. Fluorinone plus benzoic acid plus benzoic acid. And one more. Okay, 4-to-6. As long as you understand what your markings are, it's okay. What you're going to wind up doing is throwing these pieces of glass away. We don't suggest that you keep them and tape them to your lab report, but what you will do is to copy them carefully, as we'll instruct you in a minute. Okay. All right, so I've got all of these plates, and I'm going to now put them flat on the bench top here, and I'm going to take a very thin piece of glass tube. We call these applicators. These are, by the way, very difficult to find. These are actually for drawing blood, as it turns out. They hold 10 microliters of solution, max up to a certain line. And I just draw a little bit in like this, and then I'm going to and this is fluorinone, so I'm going to put fluorinone here and fluorinone in the center of all 4 of these. You don't want to make the spot too big. Okay. And fluorinone, and one more like this, fluorinone and fluorinone. Okay, so I spotted fluorinone and fluorinone on spaces 1 and 2 on our plate, and now I'm going to take benzoic acid and do the same, except I'm going to spot positions 2 and 3. So we're going to have a sort of a pseudo mixture of fluorinone and benzoic acid in the middle. We're going to see how that separates, but we're going to have benzoic acid on the far side. Whoops, as well. There. Okay. What we try to do is to use as low a concentration as we can get away with. If you use too high a concentration, the problem becomes that the spots tend to get too big and tend to expand too much, and as a result, you don't get a good separation. Okay, and one more. I'm gonna get another tube here. That one's clogging up. Okay. Now these are actually tubes. These tubes that can be reused. I actually reuse them because they are rather expensive. Okay, so we now have on all 4 plates fluorinone plus benzoic acid, and benzoic acid. And now we're going to put these in the appropriate jars. Okay, so take these off. Now the reason, by the way, that we have the filter paper on the bottom is to prevent these plates from slipping all over the place when we put these in. Okay, so we put them in. I usually put them between my index finger and the 3rd finger and put them in slowly. Cap them up. And what we're going to do is we're going to let the solvent rise in the jar up the plate. It's going to rise by capillary action. Okay. And okay, the reason we put only 10 mils of solvent in these jars is because we are spotting about a centimeter from the, let's get that out of the way, centimeter from the bottom of the plate. And if the solvent rises above that line that we drew, that horizontal line on the plate, it's going to wash the materials into the eluting solvent. Okay, now we're just going to let these things rise, and they're going to rise according to the polarity of the silica gel and the polarity of the compound itself. Okay, and if the silica gel is much more absorbent of that compound, then the solvent needed to dissolve it and push it up the plate, then you're going to see a very low traverse up that TLC plate. If the solid doesn't cling as well to the TLC plate as it does to the solvent itself that's rising up by capillary action through the silica gel, then you're going to see a much larger amount of rise, and that particular rise to the rise of the solvent up the plate, okay, it's called the RF value. And the RF value is a value that is typical for a compound under these particular conditions. The RF value is always a number that is less than 1. So if you calculate an RF value of 1.8, you're wrong. You just flip that fraction, and you'll get about I guess 1.8 would be about 2, right? Okay, so we have to just let those go for a while, and then we will be back. Okay, our solvent has risen up to a desired level, and you got to be quick with this because hexanes and ethyl acetate are volatile materials. But once you mark the progress of the solvent front, it's called the solvent front, that's how far it went in this case, you now have a position for your spots, okay, versus how far the solvent traveled from the origin, okay, and that ratio of distant spot to distant solvent is going to be called the RF. So we're going to do these for all of these, and since it's a ratio, it's not going to be too critical when I take this out, these samples out, because it is a ratio. It's much easier to calculate that ratio, however, when you let the solvent go up pretty far. And we'll see how that works out. Okay. And if you're going to stick your hands into these jars, you really should wear these gloves. Okay. Okay, now we have 4 TLC plates. And these TLC plates, okay, are going to have the fluorinone on the first 2 spot positions, and then benzoic acid on the third. But benzoic acid is also going to be on the second position. So fluorinone and benzoic acid are there sort of as a mixture, okay, a pseudo mixture, because it didn't start out like that. But it will show you that the TLC plate can in fact separate out the very polar benzoic acid from the less polar fluorinone. And so now we're going to take these over to our TLC viewer. This cabinet here is called an ultraviolet fluorescence analysis cabinet. And what it does is to reveal the spots that we separated on the TLC analysis just a while ago. And I want to caution people about this. You'll notice along the side here, aside from the on-off button, that there is a short wavelength 254 nanometer tube that's now activated because it's been depressed, and there's a long wavelength 365 nanometer tube in there as well. You must be very careful. Never put your hands in here without some kind of shielding on your hands. Now I've got these rubber gloves that I've been using for both the experiment and for inserting these glass plates into here. do not leave your hands in here for very long, okay? Because this is enough to give you not only a sunburn, but perhaps even some damage to your skin. So you have to be aware of that, okay? And we caution you about this every time we use this particular technique. In any event, you can see here that starting with the plate on the far left, where we had just the 9-to-1 hexanes ethyl acetate, that the fluorinone, which is in lanes 1 and 2, has traversed higher up the plate than the benzoic acid, which appears here to be like little arrowheads, okay, which are in lanes 2 and 3. But notice, as we increase the polarity, the fluorinone went up the plate more than the benzoic acid. That is, the fluorinone, which was less polar, okay, had a higher RF than the benzoic acid, which is more polar. Okay, and so as we go from 9-to-1 to 8-to-2 to 6-to-4 to 4-to-6 hexanes ethyl acetate, we are increasing from left to right the polarity of the eluting solvent. Now this shows up really very well on these plates. There's also something here you can see, it's kind of a surprise to me, that there is a small amount of some very high RF material in there, probably fluorine, so that the sample that we got from Aldrich in that large container was really not absolutely pure fluorinone. And the TLC clearly shows that that's the case. But notice, as the RF, or the ratio of how far the spot traveled to that of the solvent, okay, as the RF increased, we kind of caught up with that impurity and it enveloped it. But it's very clear that the fluorinone, which is less polar than the benzoic acid, has a higher RF in just about any solvent that we can try, all the way from hexanes all the way to pure ethyl acetate. So the experiment shows that we can indeed separate two molecules, and we're going to see later on that we can use this sort of analytical information to tell us how pure or impure our separation of fluorinone and benzoic acid is going to be in what we call an extraction. Okay? So bottom line, TLC is a good analytical technique, not exactly quantitative, but at least qualitatively capable of telling you what purity molecules you're dealing with.